Hi everyone. There was one other thing I wanted to talk about a little bit, just to clarify exactly what's going on with the Rook polynomial formula. It might have been a little bit much to absorb what was going on precisely when I was going through the notes earlier, so I just wanted to clarify. So first of all, you have the Rook polynomial formula. That's what we're talking about here. And the statement is that the Rook polynomial itself, if a board can be decomposed into two disjoint subboards, then the Rook polynomial for board B is going to be given by the product of the Rook polynomials for the two subboards that are disjoint from one another. Okay, so hopefully that kind of makes sense, but I want to just go through the computation quickly here. Okay, so here's the proof. Well, first of all, you know that the Rook polynomial for board B is simply given by R0 of B plus R1 of B, X, plus etc. And similarly, the Rook polynomials for the subboards are just given by R0 of BI plus R1 of BI, X, plus etc. Okay? So this is for either board 1 or board 2. That's why I've written BI here. And also, we discovered in our notes that the Rook polynomial, or the Rook number for placing k rooks on the board B, can be computed by, okay, this is sort of the key, can be computed by placing no rooks on board 1 and k rooks on board 2 plus, okay, so that's one case where I place 0 on board 1 and k on board 2. Or what else could I do? Well, I could place 1 rook on board 1 and k minus 1 rooks on board 2. Plus, right, and you just keep on going here, and the last summand in the formula for the kth rook number for the entire board is just going to be RK of B1. This is the number of ways to place k rooks. Let me move this down a little bit. It's the number of ways to place k rooks on board 1 times the number of ways to place 0 rooks on board 2. Of course, we all know that the R sub zeros for any board are all just 1, but we just want to see everything kind of written out in full detail here. Okay, so that's kind of the first part of the proof right here. Here's the Rook polynomial for B. Here's the Rook polynomial for each one of the subboards, and here is the recurrence relation. Basically, it's not exactly a recurrence relation, but this is the relationship for the kth rook number with the rook numbers of the subboards. Okay, hopefully this formula on the right kind of makes sense to you. We've talked about that at length. I'm going to erase this right now, and so just kind of keep these in mind. These are just basic facts that we're going to be using in the proof, okay? All right, so hopefully you have that. And let's look at this. Okay, so let me move this up so you can kind of see the statement of the formula here. All right, so we want to prove that the Rook polynomial for B is the product of the Rook polynomials of the subboard. Well, the way we're going to do that is we're going to go ahead and just multiply out these Rook polynomials and see what happens. That's it. Okay. So Rx of B1 times Rx of B2. What is it? What is it? Well, it's R0 of B1 plus R1 of B1x plus etc. times, okay, you know that it's R2 of B1 x squared, etc., etc. Okay, in fact, let me just let me just write that just for good measure. R2 of B1, x squared plus etc. Again, I realize that most of the time these are going to be polynomials, that is, they're going to terminate at some point, but they actually don't have to. Combinatorialists will often look at infinite boards and think about Rook polynomials for those infinite boards. So in that case, you actually have a power series. It's not a terminating polynomial anymore. Okay, so that's why I'm just saying this thing could potentially go on forever. Okay. Okay, so R0 of B2 plus R1 of B2, x plus etc. Okay, and if you multiply this out, okay, if we multiply this out, what happens? If we multiply it out, what happens? Well, the constant term is just gotten at by multiplying the zeroth rook numbers. So that's R0 of B1, R0 of B2, okay, plus, all right, now I have to think about what x is going to be. Well, that's going to be gotten at by taking the zeroth term from B1 and the first term from the B2 rook polynomial, okay, and the first rook number for B1 and the zeroth rook number for B2. Okay, that's going to give me the coefficient of x. So it's going to be R0 of B1, R1 of B2, plus R1 of B1, R0 of B2, all of that times x. Yes? And then we realize something, okay, and look, I think you know what's going to happen with x squared. If we try to compute x squared, it's going to be R0 of B1, R2 of B2, plus R1 B1, R1 of B2, plus R2 of B1, R0 of B2. That's what's going to be the coefficient of x squared if you multiplied this out. Okay, but what are these things? Well, remember that little relationship we had. This right here, that right there, R1 or R0 of B1, R0 of B2, that is R0 of B. Okay? Want to place 0 rooks on board B? Well, then you'd better place 0 rooks on board 1 and 0 rooks on board 2. Okay? And what about this guy right here? This coefficient? Well, that coefficient is exactly R1 of B. That's R1 of B. Why? Well, once again, if I want to place 1 rook on board B, then I'd better place 0 on board 1 and 1 on board 2, or, which is why it's plus, I'd better place 1 on board 1 and 0 on board 2. Okay? And now you kind of see what's happening here. Okay, hopefully you kind of see what's happening here. So what is going to happen? Well, the constant term gotten at by multiplying the two subboard rook polynomials together is just going to be R0 of B plus R1 of B x plus, of course, you know, if I would have written the next term, you would have seen that it's R2 of B x squared plus etc. And finally, that, of course, is just the rook polynomial for the board B. And that is it. Okay? That's the proof. That is the proof. So, and once again, I mentioned earlier, there might be more than just two rook polynomial things that are multiplied together. Like the decomposition doesn't just have to be 2 disjoint subboards, it could be any number of those. Okay? So you can see right away that this rook polynomial formula is more general than it initially seems. Okay? All right. That's it for now.